Welcome back. Problem 6-86. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. Statement is determine the absolute maximum bending stress in 2-inch diameter shaft which is subjected to concentrated forces. The general bearing at A and B only supports vertical forces. So you can see this is the shaft having concentrated load of 800 pound and 600 pound. At A and B we have the general bearing which exert only vertical reaction. So you have to find the absolute maximum bending stress. The diameter of shaft is 2 inch, so its radius will be 1 inch. So let's start with the solution. So first step is that if you remove this general bearing at A, so you will be having a reaction force which is RA, and if you remove this general bearing at B, so you will be having a reaction force which is RB. I have drawn the free body diagram over here, you can see. So let's find RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So about this point B, the first moment will be this RA and perpendicular distance is 60. Here you can see this is 60 and this is producing clockwise moment, so it will be negative. So I will write minus RA into 60. The second moment will be due to this 800 pound force, and you can see the perpendicular distance is 45. This is 45 inch, and this is producing counterclockwise moment, so it will be positive. So I will write plus 800 into 45, and the third moment will be due to the 600 pound and perpendicular distance is this 30, and this is also producing counterclockwise moment, so it will be positive. So plus 600 into 30 is equal to 0. So from here you will get 60 RA will be equal to 54,000 here, and you will get this RA will be equal to 900 pound. Now you have this RA, so we will find this RB by using another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is upward 900, this 800 and 600 are downward, so they will be minus 800 minus 600 plus this RB which is upward is equal to 0. So from here this RB will be equal to 500 pounds. Now you have this RA and RB, so we know that maximum absolute bending stress is equal to maximum bending moment into C divided by I. So we need the maximum bending moment. For that we will draw the shear force and bending moment diagram. So let me draw it. For that we will take vertical lines from the end of this beam and then a horizontal line to show the length in inches. X will be in inches. Okay, let each division is of 300, so 300, 600, 900 shear force in pounds, and minus 300 minus 600. Now you can see at point A we have RA which is equal to 900, so your first point will be this one 900. Now moving from point A till this load where 800, there is no other force, so shear force will remain same. At this point we have minus 800, so 900 minus 800 will bring it to 100 at this point. So shear force will change to 100. Let 100 is this point. So shear force will change to 100 pound. Now moving from this point till the another load where applied, there is no other shear force, so it will remain horizontal. And at this point we have minus 600, so 100 minus 600 will be equal to minus 500. So shear force will change to minus 500. Let minus 500 is this point. Shear force will change to this, and again moving from this point till end there is no other shear force, so it will remain horizontal. And at the end you can see you have RB which is equal to plus 500, so minus 500 plus 500 will cause it to 0, so it will be like this. It will be like this, and this is your shear force diagram. Now we'll draw the bending moment diagram. So for that I will draw a horizontal line to show the length X in inches, and on y-axis we have movement that will be unit pounds into inch. Let each division is 10,000. This is 20,000. You can take it as per your own scale, and 30,000, so on. So first area under the shear force diagram is this area, and you can see at X is equal to 0 we have movement will be equal to 0, so first moment is 0. Now area under the shear force diagram in this area is equal to height which is 900 and the length which is 15 here, and that will be equal to 13500. So at this point we have 13500. We will look at first point 13500, so this is 10,000, so let this point is 13500. Now you can see shear force is a horizontal line with 0 degrees, so bending moment will be 1 degree higher and slope will be increasing. So we will join these 2 points. Second area under the shear force diagram is this area, and this area is equal to 100 multiplied by this length which is 15 will be equal to 1500. Clear? 15. Now 1300 plus 1500 is equal to 15,000. So at this length we have 15,000. So look at 15,000. Let 15,000 is in the mid. This is 15,000. So you can see the shear force is a horizontal line, so bending moment will be 1 degree higher and its slope will be increasing, and it will be a straight line like this. You can join these 2 points. Okay. The third area under the shear force diagram is this area, and this area is height is minus 500 and length is 30. So it will be equal to minus 15,000. So plus 15,000 minus 15,000 will bring it to 0 at this point. So we will join these 2 points because the area is negative, so slope will be decreasing and it will be a linear line. So this is your bending moment diagram. Now from bending moment diagram you can see that from BMD you can see that maximum bending moment absolute value is 15,000 pounds into inch, and we have been given a rod whose diameter is 2 inch, so radius will be 1 inch. So C is equal to 1 inch. Now for circular rod we have I, second moment of inertia, is equal to pi by 4 C power 4. So pi by 4 into C which is 1 power 4. Now you have all the values, just put it in this formula. Maximum bending stress is equal to maximum bending moment into C divided by I, 15,000 into 1 divided by pi by 4 into 1 power 4. That will give you maximum bending stress. And when you solve this you will get 19.10 into 10 to the power 3 PSI. Or in KSI maximum bending stress is 19.10 KSI. And that is the answer of this question. And this was all about this problem 6-86. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-87 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler. Statement is determine the smallest allowable diameter of the shaft which is subjected to concentrated forces. The general bearing at A and B only support vertical forces and the allowable bending stress is 22 kSi. So this is the shaft where there are concentrated load of 800 pound and 600 pound, and at point A we have general bearing and at point B we have a general bearing as well that only exert vertical reaction force on this shaft. The allowable bending stress for the shaft is 22 kSi, so you have to find the diameter D of this shaft. So let's start with the solution. So first step is that if you remove this general bearing at point A, so you will be having a reaction force which is equal to RA, and if you remove this general bearing at point B, so you will be having a reaction force which is RB. I have drawn the free body diagram of this beam, so let's find this RA and RB. So we will find this by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So about point B, first moment is this R due to this force which is RA and perpendicular distance is 30. This is producing clockwise moment, so it will be negative. The second moment will be due to this 800 and the perpendicular distance is 45 inch and this is producing counterclockwise, so it will be positive. The third moment will be due to this 60 and perpendicular distance is 30 inch and it is also producing counterclockwise, so it will be positive. And the sum of all this moment about point B is equal to 0. So I will write RA into 60, that will be minus, plus 800 into 45 plus 600 into 30 is equal to 0. So when you solve this, you will get RA will be equal to 900 pounds. Now you have this RA, so you can find this RB by using equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA plus RB minus 800 minus 600 is equal to 0. So RA is 900 minus 800 plus 600 plus RB, not minus plus 600, minus 600 because this is downward, plus RB is equal to 0. So from here you will get RB is equal to 500 pounds. Now you have this RA and RB, so we will draw the shear force and bending moment diagram that we will use later in order to find the diameter. So for that I have to take the vertical lines from the end of this beam as well as from this end, and then a horizontal line to show the length in inches. X will be in inch. On y-axis we have shear force having unit pounds. Let each division is equal to 500. Clear? So this will be 1000, this will be minus 500 and minus 1000. Okay, so the first point in shear force diagram starting from this left is RA, so RA is 900, so we'll first plot 900. So let 900 is this point. Now moving from point A till 800 load, there is no other shear force, so it will remain horizontal. Clear? And at this point we have minus 800 downward. So 900 minus 800 will bring it to 100 at this length. So let this is your 100. This point is your 100. So shear force will change from 900 to 100. This point is 900. Now moving from this 100 till this another load 6, there is no other shear force, so it will remain same. But you can see at this point we have minus 600. So 100 minus 600 will bring it to minus 500. So your shear force will change to minus 500. This is minus 500. And from this point till end, there is no other shear force, so it will remain horizontal. But at the end, you have RB, which is plus 500, will cause it to go to 0. Okay, so this is your shear force diagram. Now with the help of this shear force diagram, we will draw the bending moment diagram. So for bending moment diagram, again, I will take a horizontal line that will show you X in inch. On Y-axis, you will be having a moment that will be having unit pounds into inch. Let each division is 10,000. Or you can see, let's say this is 10,000. So this is 20,000. This is 30,000. Clear? Now, moment at the X is equal to 0 will be 0. Clear? So this is your first point. The area under the shear force diagram will give you the bending moment, and this area is 900 into length 15 will be equal to 13500 at this length. Clear? So we will plot first point 1350. So let 1350 is this point, 13500, sorry. And you can see that shear force is a horizontal line with positive area, so bending moment will be 1 degree higher, it will be a linear line, and slope will be increasing. So we will join these 2 points. The second area under the shear force diagram is this area, and this area is equal to this height multiplied by 15, which is equal to 1500. So plus 13,500 and 1500 will give you 15,000. So at this length, we will have a 15,000. So we'll locate 15,000, that 15,000 is this one. And you can see this area is a positive area, and then shear force is a horizontal line with 0 degree, so bending moment will be 1 degree higher, and slope will be increasing. So it will be a straight line. Okay. The third area under the shear force diagram is this area, and this area is equal to minus 500 into length 30 is equal to minus 15,000. So plus 15,000 and minus 15,000 will cause it to 0 at this point. And we will join these 2 points using a straight line because the shear force is a horizontal line with 0 degree and its area is negative, so slope will be decreasing. So this is your bending moment diagram, BMD. Now from BMD, we will get maximum bending moment, and that maximum bending moment is 15,000 pounds into inch. And we know that allowable bending stress is equal to maximum bending moment into C divided by I. If we want to write in terms of D, so maximum bending moment into C is equal to, C will be equal to 2D by 2 because D is equal to 2C. So C is equal to D divided by 2. So if we replace C with D by 2, so D by 2. And second moment of inertia of our circular rod having radius C is pi by 4, C power 4. So if we replace C with D by 2, so D by 2 whole power 4, and that will be equal to pi by 64, D power 4. So I will write I is pi by 64, D power 4. Okay. Now, we have allowable bending stress that is 22 kSi, so I will write allowable bending stress is 22 into 10 to the power 3 pound per square inch. Clear? And from here you will get d cube is equal to maximum bending moment into divided by pi by 32 into 22 into 10 to the power 3. Clear? Or you can say it will be equal to 32 maximum bending moment divided by pi into 22 into 10 to the power 3. Clear? You can take cubic root on both sides, so you will get this d will be equal to 1.908 inch. Or you can say d is approximately equal to, you can for safety you can take diameter 2 inch diameter. And that is the answer. And that was all about this problem 6-87. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Again, thank you for watching and supporting me. Welcome back. Problem 6-27. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and movement diagram for the beam. So you can see this is an overhanging beam and there is a triangular load of magnitude W0 at this end load is 0. There is a roller support at A and at point B we have plane support. So you have to draw the shear and movement diagram for the beam. So let's start with the solution. So first step is that if you remove this roller support at point A, so you will be having reaction force offered by this support on this beam will be RA, and if you remove this pin support, so there will be a vertical reaction force of RB on this beam by this support. So first we will find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0 and taking the counterclockwise moment as positive. So you can see one load is RA, the second is RB, and the third one is if this triangular load is converted into point load, so it will be equal to W1/2 into W0 into the length over which act, and this total length of the beam is equal to L. This is L because 2L/3 plus L/3 is equal to L, and that will act at a distance of L/3 from point B or from denser side. So this will be L/3. Now we apply this equation of equilibrium. So RA into perpendicular distance is 2L/3. Let me show you. This is RA, and about point B, this perpendicular distance is 2L/3, and this is producing clockwise, so it will be negative. So I will write minus the second moment that is produced due to this load, and perpendicular distance is L/3. Clear? And this is producing counterclockwise movement, so it will be positive. Here I have L as well because it is acting over length. So plus 1/2 this load, which is 1/2 W0 into L. W0 into L, and perpendicular distance is L/3 is equal to 0. So from here we will get minus 2 RA L divided by 3 plus 1/6 W0 L square is equal to 0. So you will get 2 RA L/3 is equal to 1/6 W0 L square, and when you calculate RA will be equal to W0 L over 4. So this is the value of RA. Now we'll find this RB by using equation of equilibrium, that sum of all force along y direction must be equal to 0 and upward force is taken as positive. So RA and RB are upward, so RA is W0 L/4 minus this force, which is W1/2 W0 into L plus RB is equal to 0. So if you take LCM, so this will be 4, so it will be W0 L minus 2 W0 into L plus RB is equal to 0. So this will give you 4 minus W0 into L plus RB. So from here you will get this RB will be equal to W0 L over 4. Now you have RA and RB. So what we are going to do is that we will cut the beam at this and at this section, that this is section AA and this is section BB, and we will find the equation of shear and moment as a function of x. Clear? And then we will put the value of x to find the shear and moment, and then draw the shear force and bending moment diagram. So first step is that if you cut this beam over here, clear, and let this distance is x, this is section 1, and draw the free body diagram. So let me draw it first. Let this is the beam, clear, and you will be having a triangular load. Clear? This is the triangular load. This is the distance x where you cut this beam, and when you cut it, you will be having a shear force V, and you will be having moment M. This is your point 1. Clear? Now you can see that here the load is W0. So if you take the ratio, we have two similar triangular. One is this one, and the other one is this one. So this is for the length of L, and this is for length of x. Clear? So by using similar triangles, if I take the ratio, this W0 over length L, W0 over length L will be equal to, here let the magnitude is W. So W divided by this distance x. So W divided by x. So here we will find W will be equal to W0 into x divided by L. So here the magnitude will be W is equal to W0 into x by L. Now when you convert this triangular load into point load or concentrated load, so it will be equal to 1/2 this load, which is W0 x over L, and the length over which act, and that length is x, and that will be acting at a distance of x by 3 from this point 1. Now we'll find this V and moment by using equation of equilibrium. So first equation of equilibrium is that sum of all force along y direction must be equal to 0 and upward force is taken as positive. And remember that section AA is for x is greater or equal to 0 and less or equal to L/3. So x start from here is equal to 0, and at here you can see x is L/3. So this equation will be valid for this region. Clear? Now V is downward, so minus V minus this load is downward. So minus 1/2 W0 x square over L is equal to 0. So from here you will get V is equal to minus W0 x square over 2L. Let this is your equation number 1. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, the one moment is due to this, which is this load into perpendicular distance is x by 3, and this is producing counterclockwise moment, so it will be positive. And this external moment which we have taken as this will be positive. Now you can see that this load is producing counterclockwise moment, so in order to balance it, it will be in this direction. So let me correct it. This direction is this. So this minus moment, which is clockwise, plus 1/2 into W0 x square over L into perpendicular distance is x by 3 is equal to 0. So from here you will get this moment will be equal to W0 x cube over 6L. Clear? And this will be your equation number 2. So this equation 1 and let me write it, equation 1 and 2 are valid for x is greater than or equal to 0 and less than L by 3. Now what we will do is that we will cut the beam at any region, that this is section 2, and this region is x is greater than or x is greater than L by 3 and less are equal to L. Clear? And we will draw the free body diagram. So let me draw it over here. So this is the beam. Here there is a triangular load over here. Clear? This is the triangular load. At distance of L by 3 we have RA. So this is L by 3 and this is RA, and RA is W naught L over 4. And the total distance from this till the end of the beam is X, where we have cut this beam. So the remaining will be equal to X minus L by 3. And what about the magnitude over here? It will be the same, just like W naught X over L, because you can see you will have a two triangle, similar triangle. One is this one and the second one is this one. So W naught over L is equal to W over X, and this W will be equal to W naught X over L. Okay, W naught. So when you cut it, you will be having a shear force, clear, like this, and you will be having a moment that will be counterclockwise. Why? Because you can see now you have this force and this force as well. So we have taken it counterclockwise because its effect will give you a positive moment. Okay, so this is your point 2 because it is section at point 2. So when you convert this triangular load into a point load, so it will be equal to 1 over 2 this load, which is W naught X over L, clear, and it will act at a distance of X by 3 because X is the total length. It will be X by 3. Now we'll find this by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. And remember that this is for section 2 and here X is greater than L by 3 and less or equal to L. Clear? So W naught L by 4, which is acting upward, clear, minus this load which is downward, minus W naught X over L, clear. So this load here you can see 1 over 2 this load into the length over which that is X. So it will be W naught X square minus W naught X square over L, clear. And the last thing is that minus V is equal to 0. So from here this V will be equal to minus it will be equal to W naught L by 4 minus W naught X square over L. Or you can say this V is equal to minus W naught X square over 2L. Here you can see you have 2 as well, so it will be minus 2. Clear? So minus W naught X square over 2L plus W naught L by 4. This is your equation number 3. Now we'll find movement by using equation of equilibrium, that sum of all movement about point T is equal to 0 and taking the counterclockwise movement as positive. So about point 2 first movement is due to this W naught L by 4 and perpendicular distance is X minus L by 3. This is producing clockwise movement, so it will be negative. So I will write minus W naught L by 4 into perpendicular distance is X minus L by 3. The second moment will be due to this load and perpendicular distance is X by 3 and it is producing counterclockwise, so it will be positive. So I will write this load which is plus 1 W naught X square over L into perpendicular distance is X by 3 and there is external moment which is positive. Their sum must be equal to 0. So when you solve this, you will get this moment will be equal to minus W naught L over 4 into X minus L by 3 plus W naught X cube over 3L. Okay, just wait a minute. This is W naught X square over W naught X square over 2L. So this will become equal to 6L. Okay, now it's okay. This is your, this will be positive, M will be equal to, this will be positive and this will become negative. Okay, so this is your equation number 4. Now we have equation 1, 2, 3, 4. This equation 3 and 4 are valid for X is greater than L by 3 and less or equal to L. Clear? Now we move to draw the shear force and bending moment diagram. For that I have to copy these equations. Let me copy these equations, some portions, so that we can move toward next page. I will copy it and move to second page and will paste here. Okay. So for shear force and bending moment diagram, I have to draw vertical lines from the end of this beam. You can see here, and there is a horizontal line to show the length in X, which is not known either in meter or in inches. So here we will draw the V. Now first, what we will do is that you have all these equations. So for X is equal to 0, put in equation number 1. Equation 1 is this one. So if you put X is equal to 0, so you will have V is equal to 0. Now for X is equal to L by 3, put in equation number 1. So what we will get if you put X replaced with L by 3, so you will get shear force will be equal to minus 1 over 8 W naught into L. You can put it and you will get this value. So this, can you correct it? This is V is minus 1 over 18 W naught into L. We can put it V is equal to minus W naught. You will replace L by 3 whole square over 2L. So that will be minus W naught L square over 18L, which is equal to minus W naught L over 18. Clear? So I will again remove this. Now for X is equal to L. Clear? So put the value, put in equation number 3. So this is your equation number 3. So when you put X is equal to 3 in that, so what you will get is that you will get V is equal to minus W naught L over 4. Now you can see that at the end you will have RB, which is equal to W naught L over 4. It means that this will bring it to 0. So in between, let me plot it as well. So at X is equal to 0, we have first point is this one. At X is equal to L by 3, which is this one. Clear? So we have V is equal to minus 18. So let minus 18 W naught L minus W naught L over 18. Minus W naught L over 18 is this one. Clear? And you can see you have RA as well over here. So which is W naught L over 4. So minus W naught L over 18 plus W naught L over 4 will bring it to 7 W naught L over 36. Okay, so you can see that this the shear force, the loading is triangular, so the shear force will be second degree curve and it will be like this. So let me join first these 2 points like this, like a curve. At this point you have plus 40, which will cause it to 7. So let 7 W naught L over 36 is this point. So shear force will change from this till this point. This is the point. Okay, now at the end we have minus 4 W naught L over 4, which let this is minus W naught L over 4, and at the end you have plus, which will cause it to come to 0. And you can see that this load is again linear load, so shear force will be a second degree curve and it will be like this. It will be like this. So we'll join these 2 points by using curve, not a straight line. I'm trying it to draw like a curve. Okay. Now here you can see the shear force is equal to 0. Clear? And you will find the location where this shear force acts, because at this location the bending moment will be the maximum. So you will find this value of x, which is not known. So what we will do is that put v is equal to 0 in equation number 3. So it will be equal to 0 will be equal to minus w naught x square over 2l plus w naught l over 4. So what we will get from here, that x will be equal to, let me check it, this will give you x square is equal to l square over 2, and x will be equal to 0.707 l. Clear? So this is x is equal to 0.707 l. So you can put this value of x in this equation number 3, so you will get v will be equal to 0. We'll move toward bending moment diagram. So for bending moment diagram, I will again draw a horizontal line, and here x will be the length, and y axis we have moment. So what we will do is that for x is equal to 0, put in equation number 2. This is equation number 2. So if you put x is equal to 0, so moment will be equal to 0. So your first point will be this one. Here moment is 0. Okay. So for x is equal to L by 3, put in equation number 2. Equation number 2. So this is your equation number 2. You can see. So if you put x is equal to L by 3, so what we will get after the calculation, or after simplifying, you will get moment will be equal to 0.00617 W naught L square. I have already done it, but for reducing the length of the video, you can do it by yourself and you will get this value. Now you can see this is a positive value. Clear? This is a positive value. So while representing this positive value on moment diagram, it will cause the bending moment to go downward. So let this point is minus 0.00617 WL square. This is a convention given in the book. And you can see that this shear force is a second degree curve, and you can see the moment is 3 degree equation. So it will be just like, it will be also a third degree curve, and the bending moment will be like this, starting from 0 till this end. Okay. Now for x is equal to 0.707 L, put it in equation number 4. That will give you maximum bending moment. This is your equation number 4. So if you replace x with 0.707 L, so you will get the maximum moment, which will be equal to 0.0345 W naught L square. So we locate this point. Clear? And this will give you the point will be like. Welcome back. Problem 6-192, that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is, a wooden beam has a square cross-section as shown. Determine which orientation of the beam provides the greatest strength at resisting the moment M. What is the difference in resulting maximum stress in both cases? So you can see this is the square cross-section having length A by A, and this is also a square cross-section A by A. But the orientation here is this, and the orientation here is like this. And they are both applied by same moment M and M. So you have to determine the orientation which provide greatest strength, and then you have to find the difference in resulting maximum stress in both cases. So let's start with the solution. So for case A, we know that maximum bending stress is equal to moment into C divided by I. So you can see here, this is moment M applied. So due to this moment, it will bend like this. Clear? So this lower portion will be in tension and upper portion will be in compression. And this is the horizontal axis, because this horizontal axis is, this will be A by 2, and this will be also A by 2. So it will be symmetrical, A by 2. So here the maximum stress will be here, and this distance C will be equal to A by 2. So maximum stress is equal to M into C divided by I. So C is equal to A divided by 2 if you take this horizontal axis. So C is the maximum distance from neutral axis till outer surface. So this is C, and this is equal to A by 2. What is the moment of inertia for this square? So it will be equal to 1 over 12. B is A, breadth is A, and height is also A. So 1 over 12 B H cube. So A cube. So I is equal to 1 over 12 A power 4. The moment of inertia formula for square is equal to, for square section is 1 over 12 B multiplied by H cube. So B here is A, and H is also equal to A. So this is the moment of inertia. So put all these values in this formula. So maximum bending stress for case A is equal to moment C is equal to A divided by 2, and I is 1 over 12 A power 4. So when you calculate it, you will get maximum bending stress comes out to be 6M divided by A power 3. So this is the maximum bending stress for case A. Now we'll move toward case B. So for case B, we have same formula. Maximum bending stress is equal to moment into C divided by I. Now you can see if I draw horizontal line, clear? So it will form 2 triangles. I take horizontal line from here, it will be 2 triangles. Clear? So this side is A, this is also A. Clear? So this distance by using Pythagoras theorem, that this is point A and this is point B. So AB will be using a Pythagoras theorem. AB square is equal to A square plus A square, which is equal to 2A square. So AB will be equal to under root 2A square, which will give you under root 2 times A. And this AB will be equal to 1.41 times A. Clear? If I draw a vertical line from this top, this line, and this is point O, so and this is point C, so CO is perpendicular, so CO will be equal to, again you can see this is also same over AB, so it will be equal to AB, this distance will be equal to CO will be equal to AB divided by 2. So CO is equal to AB divided by 2, which is equal to 0.707 times A. Clear? Now CO, from here C is the maximum distance from neutral axis till the topmost or bottommost. This is equal to C, this is also equal to C, so bending stress will be maximum over this because this point is in tension. So C is equal to 0.707 times A. Now moment of inertia I for this rectangular portion, since there are two rectangles, so the moment of inertia is 1 over 36 bhq, and this area by using parallel axis theorem, its centroid will be away from this neutral axis. Clear? So we will write AD square. So I will write 2 multiplied by 1 over 36 bhq plus AD square. Clear? So what is B here? So B is this AB. B is equal to this AB, which is equal to 1.41 times A. What is height? Height is equal to CO, and that is equal to 0.707 times A. Clear? And what is area? So area will be equal to, for this triangle, is equal to 1 over 2 breadth into height. So 1 over 2, not 1 over 12. So this is 1 over 2 B into H. So B is 1.41 times A, and H is 0.707 times A. And D is distance from neutral axis till the mid of this section, till the centroidal of this section. And for this triangle, its centroid will be equal to 1 over 3 of CO. CO is this distance. So 1 over 3, its C will be, I will choose another color, its C will be this one, and this distance is equal to, 1 over 3 times CO. So 1 over 3 times 0.707 times A. Now you have all the values. This D, this is equal to D. So D is equal to 1 over 3 times CO, and that is 1 over 3 times 0.707 A. Now you have all the values. You can just put it in this formula. Clear? So you will get I. So I will write I is equal to 2 times. Why 2 times? Because we have two triangle. One is this one, another one is this one. So 2 times 1 over 36. Clear? B breadth base is this one AB, which is 1.41 times A, and height is CO, which is 0.707 A power 3, plus 1 over 2, which is the A, plus A. A is equal to 1 over 2. This is A. We have calculated 1 over 2 into 1.41 A into height is 0.707 times A into D square. So D is 1 over 3 into 0.707 A square, whole square. So when you calculate this I, so this I will be equal to 0.0833 A power 4. Now you have C, you have I, so you can put it in this formula. So you will get maximum bending stress will be equal to M into C divided by I. So M, C is 0.707 times A divided by I is 0.0833 A power 4. So when you calculate it, you will get the maximum bending stress comes out to be A power, 8.4853 times M divided by A cube. So this is the maximum bending stress for case B. Now you can see you have, this is for case A, and this is 6M, and this is for case B. So for applying the same moment over these two different orientation, this gives 6M, bending stress comes out to be 6M over A cube, while this give you bending stress is 8.4853 M over A cube. Since this value is smallest stress, so it means that the same moment is producing smallest strength as compared to here. Clear? So the safest or highest strength will be the case A. Clear? So I will write it over here. So case A provides higher strength since the resulting maximum stress is less for a given moment and A. Clear? You have seen that both have same M and both have same M A. So this is giving you the maximum bending stress here is less than maximum bending stress over here. Clear? So it means that this is producing maximum strength too, or it is resisting this moment greatly. Okay. Now we'll move towards second part. What is the difference in their stress bending stress? So difference in their maximum bending stress is this one is higher. So 8.4853 M over A cube minus the second one is 6 M over A cube. So you will get this maximum bending stress comes out to be 2.49 M by A cube, which is the answer of this question. I hope you have enjoyed this video, and that was all about this problem 6-192. If you have any question, you can ask me in comment section, and do subscribe my channel if you are new to it. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 6-193 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and movement diagram for the shaft if it is subjected to vertical loadings of belt, gear, and flywheel. The bearing at A and B exert only vertical reaction on the shaft. So you can see this is the shaft, and this is bearing A and B that exert only vertical reaction. Clear? This is the gear where there is a 450 Newton load. There is a flywheel or belt. You can see this 300 Newton, and there is a flywheel which have 150 Newton. So you have to draw the shear and movement diagram for the shaft. So let's start with the solution. So first step is that if you remove this bearing at A, so you'll be having a reaction force. Let this is RA, and if you remove this bearing at point B, so you'll be having a reaction force force which will be equal to RB. This distance is 200 millimeter or 0.2 meter. This is 400 millimeter or 0.4 meter. This is 300 millimeter or 0.3. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, the first moment will be 450 into perpendicular distance is 0.2. When this is producing clockwise, so it will be negative. So I will write it minus 450 into perpendicular distance is 0.2 meter. The second moment about point A is this 300 Newton load and the perpendicular distance is 0.6 meter. And this is producing counterclockwise movement, so it will be positive. So plus 300 multiplied by 0.6 meter. The third moment will be due to this RB into perpendicular distance is now 0.9 meter. You can add them. This is 0.9. This is counterclockwise, so it will be positive. So I will write plus RB into 0.9 meter. And the last moment that is due to this 150 Newton load and now perpendicular distance is 1.1 meter, because when you add it, it will be 1.1 meter. Okay, so we will write this is producing clockwise movement, so it will be negative. So I will write minus 150 into 1.1 meter, and this will be equal to 0. So when you solve this from here, you will get this RB will be equal to 83.33 Newton. Now we will find this RA by using equation of equilibrium that sum of all forces in y direction must be equal to 0 and upward force is taken as positive. So RA is upward, so RA, this 450 is downward, minus 450, plus this force is upward, so it will be positive, plus RB, which is 83.33 Newton, and minus 150 is equal to 0. So when you solve this, you will get RA will be equal to 217 Newton. Now you have RA and RB, so we will draw the shear force and bending moment diagram. So what we will do is that we will take two lines from the end of this beam. One is this one and the other one is this one. There is a horizontal line to show the length that will be in meter, x in meter. On y-axis, you will be having a shear force having unit Newton. Okay. So we'll take one division is equal to 50. So this is 50, this is 100, this is 150, this is 200. Similarly, minus 50, it will be minus 50, minus 100, minus 150, minus 200, and minus 250. So we'll first draw the shear force diagram. Now at this point, you can see you have RA, which is 217. So we'll locate 217. That this point is 217 Newton. So moving from point A till this load, there is no other shear force, so it will remain horizontal till this point. Okay. Now here we have minus 450 Newton that is acting downwards. So 217 minus 450 will cause it minus 233 Newton. So at this point, the load will be minus 233. So let 233 is this point minus 233. So your shear force will change from 217 to minus 233. And moving from this load till this mid, there is no other shear force, so it will remain same horizontal till this point here, and we will draw a horizontal line. Okay. Now at this point, you can see you have plus 300 upward, so minus 233 plus 300 will cause it to move to 66.7 Newton. So the load will be 66.7. So that 66.7 is this load, this point, 66.7. You can choose your own scale as well. Okay, this is 67. Now moving from this mid till point B, there is no other shear force, so it will remain same horizontal till this point. So we will draw a horizontal line till this point. And again, you can see you have plus RB. So 66.7 plus RB is 83.33 will be equal to 150 Newton. So shear force will change to 150. So this will move to this point. This point is 150 Newton. And moving from 150 till end, there is no other shear force, so it will remain horizontal. And at the end, you can see 150 that is downward. So plus 150 minus 150 will bring it to 0. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for that, again, I will need the space. So let this is your horizontal line to show x in meter. And here you have moment. Let each division is 25. So this is 50. Similarly, minus 25 and minus 50. Okay. At point x is equal to 0, we have moment is equal to 0. So your first point will be this one. Now first area under the shear force diagram is this area. And you can see this area is, this height is 217 and this width is 0.2. So 217 multiplied by 0.2 is equal to 43.3 Newton into meter. So we'll look at 43.3. So let this is 43.3. This point is 43.3 Newton into meter. The unit is Newton into meter. And you can see shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher and slope will be increasing. So we join these 2 points using straight line. Now the second area under the shear force diagram is this area, and this area is equal to minus 233 multiplied by this 0.4, and this will be equal to minus 93.3. So plus 43.3 minus 93.3 will cause it to minus 50 at this length. So we will plot minus 50 at this length. So minus 50 is this point. Okay. Now this shear force is a horizontal line with 0 degree, and this area is negative. So bending moment will be 1 degree higher and slope will be decreasing. So we'll join these 2 points using a straight line. This is minus 50. Now moving further, the third area under the shear force diagram is this area, and this area is, you can see, height is 66.7 and this width is 0.3, and that will give you 20.01. So minus 50 plus 20.01 will cause it to minus 30. So at this length we will be having minus 30. So we plot minus 30. So let minus 30 is this point. This is minus 30. And you can see this shear force is a horizontal line with a positive area. So bending moment will be 1 degree higher and slope will be increasing. So we'll join these 2 points using a straight line. The last area under the shear force diagram is this area, and this area is 150 multiplied by this 0.2, which is equal to plus 30. So minus 30 plus 30 will be equal to 0 at this point, and we will get the bending moment like this. We will get a straight line, and the slope will be increasing because the shear force area under the shear force is positive area, and this is a 0 degree line. So this is your bending moment diagram. And that was all about this problem 6-193. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-194. This problem is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbler. So statement is the strut has a square cross section A by A and is subjected to bending moment applied at angle theta as shown. Determine the maximum bending stress in terms of A, M, and theta. What will be the angle theta will give you the largest bending stress in stress. Specify the orientation of neutral axis for this case. So this is a square strut having side A by A and is applied with a moment here at angle theta from the Z axis. So you have to find the maximum bending stress in terms of A, M, and theta. You have to find theta for the larger bending stress and you have to determine the neutral axis for this case. So let's start with the solution. So you can see that this moment is applied at angle theta from this axis. So it will have, if we resolve it into two components, so the first component will be this one and this component will be like this. This component will be equal to m cos theta and that will be minus because it is opposite to z. And similarly it will having a vertical component like this. So this will be equal to, again this will be minus m sine of theta because it is opposite to y. Clear? And this will be in this direction. So if I write it over here, so this will be the vertical component will be like this. Okay, so vertical component will be like this, minus m sine theta. Now let this is your point A. We will specify these 2 points and this is point B. So you can see this is z axis and this is y axis. So this is moment about z. So I will write it is equal to mz and this is moment about y axis. Clear? So it is moment about y. So due to moment about z, clear, this is like this. This will be like this, causing this surface to bend like this. The upper portion, this point A will be in tension, and due to this moment about y, it will also cause it to bend like this. So you can see point A is in point A is the position where we will have maximum bending stress. So we will find this bending stress. So we will write this mz is equal to minus m cos of theta and this my will be equal to minus m sine of theta. We will find section properties, which is the second moment of inertia for this strut, and this moment, second moment of inertia I about y-axis is equal to I about z because this is square strut. So we have 1 over 4, 1 over 12 bh cube. So b is a and h is also a. So 1 over 12 a power 4. So this is 1 over 12 a power 4. Now for maximum bending stress, I will write the formula. Maximum bending stress, as I have already discussed, that maximum bending stress will be at point A. So it will be at point A. So what is the formula for? Now the stress that will be due to this moment about z axis and due to moment about y axis will be a combination of both this. So I will write stress is equal to, first due to moment about z. So I will write minus m into z multiplied by y divided by I double z or iz and minus m into y into z divided by I y. Why? You can see for this case, this is moment about z axis. Clear? So this vertical distance, we know that the stress due to this will be equal to moment into y into distance. So this distance is in y direction. That is why we have taken this I, and I is about z axis. Similarly for this, you can see that this is the moment my and this distance is in around z direction. So I about this y axis. Clear? So that is why this formula. Now we'll expand this. So we will write minus mz is minus m cos theta. So minus m cos of theta. What is y? Since point A is in positive direction of y, so it will be equal to, this total distance is a. Clear? So this will be equal to a by 2. So I will write a by 2 divided by iz is 1 over 12 a power 4 minus this moment about y is m minus m sine theta. So I will write minus m sine theta into this distance, which is also again a by 2 from this y axis, Okay, so I will write into a by 2 divided by 1 over 12 a power 4. So again, when you solve this, you will get sigma is equal to 6m over a cube into cos of theta plus sine of theta, which is the maximum bending stress in terms of a, m, and theta. So this is the answer of our first part. Now we'll find the second part, in which we have been asked to find the theta for the largest. So if we take the derivative of d sigma over dt and make it to 0, so you will get the angle. So let's take d sigma over d theta in equation 1, answer of 1. So you will get d sigma over d theta will be equal to 6m over a cube into d over d theta into cos theta plus sine theta. So from here you can see that this d sigma over d theta should be equal to 0. So 0 is equal to 6m over a cube, and derivative of cos theta is minus sine theta. Clear? D cos theta, derivative of cos theta is minus sine theta plus derivative of sine theta is cos theta. And from here you will get cos of theta minus sine of theta is equal to 0. Clear? And theta will be equal to 45 degree. Why? Because cos theta is equal to sine theta. So if I divide sine on both sides, so cos on both sides, so you will get 1 is equal to sine theta divided by cos theta. So we will get sine theta over cos is equal to tangent of theta is equal to 1. So if you take theta is equal to tangent inverse of 1, so you will get 45 degree, which is the answer of our second part. And in last part, we have to define the orientation of neutral axis So for that we have formula that tangent of alpha is equal to Iz over Iy into tangent of theta. Since Iz and Iy is 1 over 12 a power 4 into divided by 1 over 12 a power 4 and tangent of 45 degree. So this will cut with this and we will left with tangent of alpha is equal to tangent of 45 degree. So alpha is equal to 45 degree, which is the orientation of neutral axis for this case. So if I draw the orientation of neutral axis, so it will be like this. At 45 degree you will take the orientation. So this is alpha, which is equal to 45 degree. And that was all about this problem 6-194. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.